In this video, let's look at the work energy part 2. Work energy part 2. And in the first part, we derived the work energy that U122 equals T2 minus T1. Now let's look at the work can be done by different type of forces. The first force we're going to look at is the weight force. Weight force. And imagine if we have a particle P that is falling down, has the weight force W and has the height H. And if we can set up a Cartesian coordinate system as I and J, right? And since the work energy equation was derived from the path coordinate system, so we do want to have the ET hat inside of our system. ET hat is tangential direction, unit vector. It points to the direction, the motion of direction. Therefore, if we need to add ET hat goes along the vertical downwards, same direction as how this particle P falls. Okay, this is P. Okay, if we have these two coordinate systems, in this system, ET hat and J hat are both on the vertical direction but has the opposite direction, which means if we do the conversion between these two unit vectors, and our ET hat equals to negative J hat, right? And the displacement on the ET hat direction, which is what's the distance this particle T over falls, ds, equals to negative dy, because in xy we define that is y direction, I is the x direction. Okay, with knowing this, let's write down the weight force W. W can be written as mass times acceleration, right? F equals am, and this we can write A as g, gravitational acceleration, g. What direction? If we want to write everything in terms of I and j, we can write this definitely on j direction. It's moving downwards, so it's negative j direction. Okay, this is our force, and this expression for the force, let's use force energy. And the derivative of the force, copy that, negative mg j times ET hat times ds, okay, equals v2 square over 2 minus v1 square over 2. Okay, sorry about my writing. You may have questioned, where does this come from? So this is our force, right? And this is our unit vector dt in ds. That's from the work energy equation. Sum of the forces dot ET hat times ds. On the other side is m v2 square minus v1 square over 2. Okay, let's get back here. Because here we know the translation between ET and J and ds and dy, we can substitute this into this expression. Then we end up with negative mg j, replace ET with negative j, replace ds with negative dy, whole thing equals m v2 square over 2 minus v1 square over 2. Okay, if we can simplify this, we'll end up with u 1 to 2, the work done by the position from position 1 to 2 equals by the weight force equals negative mg h1, that's a position height 2, sorry, minus h1. Let's trace this, h2 minus h1 equals v2 square over 2 minus v1 square over 2. Okay, now we have expression of weight energy equation from a weight force. If we look at this equation, the work energy equation from weight force, we'll find out this equation relies on the information from position 1, position 2. The height of position 2, position 1, and the velocity at position 2 and position 1. So, which means it only depends on the endpoints, but not path. Depends on the endpoints. Not the path. Okay. So if this is the case, if a work done by a force only depends on the endpoints, not the path, we call this type of force conservative force. Okay. And we can write the work needed as the potential energy by using the capital V. So potential capital V by the weight force equals mgh. Mass, gravitational acceleration, and h, displacement on vertical direction. Okay, so that's the first analysis of work energy equation by weight force. Now let's look at the second force, normal force. Oh, sorry. Let's change colors. Okay. Normal force. What is normal force? Normal force is really perpendicular to the supporting surface, right? And usually has the perpendicular to the motion of the particles. So if we have a block A sliding on a surface, block A. Now we have wave force, we have normal force. And normal force, the work of normal force, if we can write down normal force, and times ET hat equals 0. Why normal force times dot product ET hat equals 0? ET hat would always pointing to the motion of the particle of, right? In this case, the particle, which is this block, is moving to the right, so your ET is pointing to the right. And where's your En hat? Where's your normal force? Your normal force is pointing upwards, vertical. You only have normal force on vertical direction, and it has zero. It has zero components on ET direction. Therefore, NT, no, ET hat dot product N, which is normal force, equals 0. So that tells us any force perpendicular to the motion do not contribute to work. So let's see. Perpendicular force do not work. And here perpendicular means perpendicular to the motion. Keep that in mind. Okay. Next, I have one more force to introduce. That is spring force. Spring force here. And spring force is also a conservative force. And the work done by the spring force can be expressed by U122 equals E cosine equals K over 2. That's a spring constant. Parentheses negative L2 minus L0 L square plus L1 minus L0 square parenthesis. So L0, it's a length when it's unstretched. And L1 represents the length when stretched at position 1. L2 is the length when stretched at position 2. So we can write the potential force as the big capital V by the spring. Let's add a superscript for spring equals K over 2 times L minus L0 square. And the L minus L0 or L naught, it's delta L, the change of length. Okay, so far we have 3 conservative forces: normal force, doesn't do any work, and wave force and spring force. And next time we're gonna learn what is a non-conservative force. Alright, thanks for watching.